Hello everyone and welcome to this new video where we discuss mathematics and physics on the board. In this video we are going to discuss a very simple or at least fundamental topic which is basically how do we evaluate the the expression of the derivative of the inverse of a function if we know already basically the expression of the derivative of that function. So that's what we are going to do today. Right, okay, so just to put a little bit things in context, usually when people derive or teach the kind of derivatives, often you're going to look at very simple derivatives that you can get from um, the like the basic rule of the limit of the difference and then divided by h when it tends to 0. But then often this leads to just a handful of cases that people do, in some practice exercise or something like this. But then the point is, how do we know then for all the rest of the functions? And as it turns out here, I'm just going to provide a technique where I explain how you get the derivative of a function if you know basically the derivative of its inverse, okay, and vice versa. All right, so the context here is as follows. So let's say you've got a function f, and this function maps a domain that I'm calling df, so that's a domain of definition of that function, and then onto a codomain or an image space of f. Okay, so that's basically kind of characterizing of this function. And basically, from a notation perspective, you basically take an argument x that belongs to that domain, and then it returns a number f of x that belongs to that codomain. Now, here what we require as well is that there is a one-to-one relation between x and f of x. So what this is going to mean is that the function here is bijective on this particular all interval. Now, the inverse function can be viewed here as an f, and then I've put basically an index here -1 to basically signify that this is the inverse function of f. Now, sometimes people are going to put the -1 as an exponent. Now, this is, if it's not specified at some point somewhere, then that can be misleading as being 1 over f. Okay, so that's the reason why here I've decided to put it as an index, because basically it's a bit less ambiguous what I mean. So by definition, essentially this is going to return some element which is in the codomain of f, and then return something that is in the domain of f. Okay, that's what the inverse is going to do. If you know f of x, you want to be able to know to infer x from the inverse. Okay, and so the question we ask is basically, given f prime of x, what is then going to be f -1 prime of x? Okay, so let's see how these things work. It's really very quick to derive. So the idea is to say that, well, by definition, so that's really the definition of the inverse. And the definition is the following. You're going to have that f -1, and then if inside f -1 you put as an argument, instead of x, you put f of x, then it has to return that this is equal to x, sorry. It has to be equal to x, because that's the definition of an inverse. If you then, basically, if you apply the inverse onto the function itself, then it has to return x. So just basically that's what it is. It kind of cancels out what the function f is doing. And what we can say, therefore, is that if I'm looking at the derivative with respect to x of that object, okay, then this is going to be x prime, if you will. and x prime, so the derivative of x, and this is equal to 1. Okay, as you know, everybody knows the derivative of x is 1. So again, what is really crucial is a starting point of the inverse function, and then once you've got that, then you just say that. Okay, so that's the first aspect. But then we have also that by the chain rule, okay, we have the following. We have that f minus 1 of f of x, and then I put here prime is equal to f minus 1 of prime of f of x, and then times f prime of x. Okay? And so this, therefore, when you put these two together, you end up with, therefore, we have that f minus 1 prime, and then of f of x times f prime of x is equal to 1. And it follows, therefore, that f minus 1 prime, and then I'm simply going to call f of x, I'm going to, well, let's continue actually, let's put f of x here, and then this is going to be 1 divided by f prime of x. Okay, now the thing is that I want to know what is f minus 1 prime of x. So what I'm going to do is simply change the name of the variable. So f of x, I'm going to denote that like this. So I'm going to denote this, for example, u, okay? And therefore, I've got as well that x is equal to f minus 1 f minus 1 of u. Okay, so so basically that's the idea. So it's u, the x that is evaluated here is f minus 1 of u, and so in the end we end up with f minus 1 prime of the variable u is going to be 1 divided by, and then that's f prime of f minus 1 of u. Okay, so that's kind of the general formula here. And what we are going to do is simply look at an example and see how that works. And in particular, an example that is not necessarily always treated, but that we need to know when we integrate. So often, the first time we are going to see that is when we work on trying to evaluate various integrals, and sometimes kind of difficult, and you need to know essentially the expressions of the derivatives of, for example, arctan, arcsine, and so on. And so here we are going to see how to find one of these. So the way it works is as follows. So we are going to look at an example. And the example I'm going to choose is f of x is equal to tan h. So that's the hyperbolic tangent of x. And so f minus 1, therefore, is going to be f minus 1 of x is arctan h of x. Okay, now as it turns out, the hyperbolic tangent of x is basically defined from, that goes from r, so on all the reals onto the interval minus 1, 1. But basically that's kind of the idea. So if you want, we can just specify that df is equal to r, and then co-df is equal to the interval minus 1, 1. And in any case, we want to know, so we also need to specify what is f prime of x. Now, so this I'm going to leave you with trying to evaluate that, but the standard example is that this is 1 minus hyperbolic tangent squared of x. Okay, this is in comparison with the 1 plus tan squared that you would get for a tangent. And basically that's it. So now what we are going to do, so we've got f prime of x, and so what we are going to do is the following. So we apply the formula. So f prime minus 1 of u is equal to, and that's 1 divided by f prime of f minus 1 of u. So let's actually put that in. So this is 1 divided by, and that's 1 minus tan h, and the tan h is actually of arctan of x, and then that's squared. And as it turns out, tan h of arctan h, sorry, that's arctan h. So that's arctan h of x. And so this is simply returning x by definition of the inverse. And consequently, we get that this is, of u here, arctan of u. And so we get that this is 1 divided by 1 minus u squared. Okay, and so this is very useful again, because you may find out sometimes that you've got some integral to perform of, for example, dx over 1 minus x squared, and somehow you're supposed to know by heart that this is basically arctan prime, so that's the derivative of arctan h, but actually that's one way to get there in case you're not sure what the answer is. So from this, the conclusion is that arctan h prime of x is equal to 1 divided by 1 minus x squared, which again is very useful when integrating. So one of the things you can do once you have this particular strategy is to try to see how that works for other functions, maybe simpler ones, and see whether you retrieve the formulas that you've seen in various books, or maybe in fact that you've never seen before. So you can try to discover these things. Now, if you've got any questions or comments, please do let me know in the comment section, and otherwise we'll see each other in the next video.